So in the last lecture, we talked about the exploration for linear function approximation. Sorry, just one second. In the last lecture, we talked about exploration. With linear function approximation. And in particular, we talk about two algorithms. One is the standard least square value iteration with upper confidence bound. The other one is Elena. Essentially, we talk about this is like using local optimism, and this is using global optimism. So we only talk about the algorithm in the last lecture, but we can essentially also talk about the guarantees. So in terms of regret, we mentioned UCB VI, LSVI UCB. The regret is like O tilde square root of d cube h cube t. Okay. And we didn't get time to talk about the guarantees, but for Elena, we can similarly get a regret. But a regret is slightly better. Is d square root of h cube t. Okay. So instead of square root of d cube, which is like out of square root is like d to the 1.5, this is like just d, linear in d. So in this case, Elena's regret is actually better. The reason we also kind of said in the last time, local optimism require a strong condition, which kind of require at every stage your value is like an upper bound. So this inevitably make the bonus quite large and eventually make the regret also large. On the other hand, for global optimism, you don't have like this artificial constraints, so you can make the bonus very tight. And in the end, your regret is also better. So we can do the following comparison. So essentially, we first talk about assumptions where in the LSVI, we require linear MDP assumption, which is stronger. While in the Elena, we only require the linear completeness. We say the linear MDP is a special case of linear completeness. So in the sense, the assumption is weaker. Also, in terms of sample complexity or regret, we already mentioned earlier. This local optimism is a bit loose in terms of bonus, so this is like worse. And Elena is actually much sharper in the bonus, so this both sample complexity and regret is better. And finally, in the very last, very end of the last lecture, we also talk about the drawback of Elena is essentially the computational complexity. In which case, the local optimism is actually better because we have some specific form of a bonus, and we can add to each stage. While in Elena, because we have the tighter bonus or tighter this regret, so we need to solve a very complicated optimization problem and optimize over policies within a very complicated constraint set, confidence set. So this is like very difficult. So this, in fact, is like inefficient. Inefficient in the sense there is no, we don't really know any polynomial time algorithm solving for this scenario. So finally, I also want to comment that there is another drawback of local optimism, is this we require the specific design of bonus function. In a sense, if you still remember in the linear function class, we kind of like said in the last lecture, the bonus is in the form of this like lambda phi transpose lambda inverse phi, where phi is a grand matrix. This lambda is grand matrix, phi is the feature vector. And this type of bonus is very specific to linear structure. And this is actually very difficult to generalize to generic function approximation beyond linear case. And this is why today when we talk about general function approximation, we will actually prefer the global optimism, because there, if you remember, the construction of the confidence set is basically just saying my parameter need to be close to the empirical average, and that's it. We don't really design what is the bonus function, and we will see there's a generic way of designing that kind of a global confidence set, okay? So this is actually a drawback. You need like very particular design attuned to the structure of function. Okay. So this is just a brief recap of what we have been talking about in the last lecture. So today we will move beyond the linear setting, and we talk about the generic function approximation. Of course, when we use like reinforcement learning in practical applications, for example, we solve video games like Atari, like StarCraft, or we want to do some robotics task, like doing some simulation, local motion, or like manipulation. Linear function approximation in general is not sufficient. Like we usually use neural networks to approximate the value or a policy. Like neural networks, you all know, it's like highly nonlinear. It's a very complex function. So that's why we always need to move beyond the linear function approximation and talk about generic setting and understand in generic what is like principal algorithm and what is the condition that required to solve this general function approximation. So let's talk about some formulation. So to talk about general function approximation, we first need a function class. Like in the linear function approximation, we have the linear function. So here, we just generically assume we have a function class. Let's call it fh, where h is from 1 to capital H. So this is, let's say this is our classes of Q functions. So fh is a class of Q functions, and we use a little h to denote so that the function class at a different step can be different. In the linear function class case, all the fh is just equal to the linear function. Okay, so this is a set of functions. That's we're assuming we're given this function class f. Maybe you can say it's a linear function. You can say it's like quadratic function. You can also say it's a class of all the possible functions represented by two-layer neural network or something like that. And then we essentially want to pick out one function out of this function class, which is the true optimal Q function. Okay. So we again consider the scenario we have an infinite number of states. But let's say we have, let's assume we have finite number of action. Or similar to least square value iteration, linear setting, we don't actually require this action to be finite, but all we require is like when we do the maximization over action, this is like solvable. Okay. And one very important quantity we're gonna use a lot is again this Bellman operator. I think we have been talking about this for quite a few times. Where we use this th as a Bellman operator. Th is a function is a function that maps any value function. Value function can be denoted as a function in the SA space. Okay. This is like a state set, it can be infinite. To so essentially, Bellman operator is a map from value function to value function, Q value function to Q value function, so that we know this THF SA is equal to RHSA plus the expectation of S prime sample from the transition and max A prime F S prime A prime. Okay, so this is essentially the basic setup for the general function approximation. All we replace is we just now have a general function class. So the first main question is what kind of structure allows sample efficient reinforcement learning? That is, we want to identify some particular structure so that we can actually do reinforcement learning in this like general function approximation scenario. So remember, in the linear setting, we have this set of results for LSVI, which require the linear MDP. And linear MDP is quite a strong assumption, which require both reward and the transition to be linear, which it's a little bit unclear for general function approximation. What does it mean? Like we require like some reward and transition in some generic function class, but how it related to this? But we have another candidate that is Elena, which this set of results, linear completeness, is very easy to generalize to the general function approximation. So we will use this approach. And essentially, we will try to generalize Elena. So the first assumption, if you still remember the linear completeness part, the first assumption we have is the realizability. It basically just says the optimal Q value, Q star H, is inside my general function class. Remember, in the linear completeness, it says Q star is linear. But here, the realizability for general function approximation is just, if I'm given two linear neural networks, then I require optimal Q value is inside this two linear, is actually can be represented by two linear neural networks. If I'm giving some function class, I require my Q star is inside function class. So this is like the realizability so that I don't have like any misspecification error. So the assumption 2 is also a direct generalization of linear closeness. So this is like a generic closeness. So generic closeness kind of like requires for any f, so for any value function in my function class, fh, I actually require, after applying Bellman operator on this f, I need it to be within the, fh plus 1. After my applying Bellman operator on this f, I need it to be inside the function class at h step. So this is, again, also a direct generalization of linear completeness, just removing the linear part. But essentially, the completeness part still remains. Whatever in the function class, after applying the Bellman operator, is still within the function class. Okay, so those are two abstract assumptions we directly get from a linear. So the question is now, does those two, are those two enough to guarantee some sample efficient reinforcement? Like, can we design some algorithm just based on those two assumptions and provide some guarantees? So we will think about this problem again from the perspective of like a standard approach where we consider the easier case like generative model first, and then talk about like online, offline scenario. So in the simulator case, it's always the easiest case. But unfortunately for the general function approximation, the simulator become a little bit hard because remember in the simulator case, in the tabular, what we do is we sweep over all state action. Which we can no longer do here because we have infinite number of states and infinite number of action. And then in the linear case, we're sweeping over some core set. Okay. Core set is, again, something a bit unclear in the general function approximation because this is kind of like it's kind of like very adapted to the linear structure because core set definition is essentially says is first is full rank, and the second thing is everything in this linear span can be efficiently represented by those bases. So if I have a general function approximation, it's unclear whether it's linear structure. So there's like we don't really talk about what is basis, what is like linear span, or that kind of stuff. So this is again very difficult. So it turns out for simulator setting, it's a bit unclear what is how we're gonna do this scenario. So what we do instead is we directly resort to the offline and the online setting to make sense. So let's first talk about offline setting. We talk about offline setting because in the offline setting, remember we can have some easy algorithm. Remember in the offline setting, in the tabular, we mentioned that there's a certain condition called all policy concentrability. Which essentially says the data we collected will cover all the visitation measure of all the policies. Okay, we will talk about the mathematical details later. But the very good thing about in the tabular setting, if we with all policy concentrability, we can actually just do value iteration. And that's gonna solve the problem, okay? That is value iteration without any modification, and that's gonna solve the problem. So let's first figure out what is the value iteration equivalent in the general function approximation, given this kind of a condition. And remember in the tabular setting, we also have like one policy concentrability, and so that we can do VI with pessimism. That's a little bit more complicated. So we will focus on this simpler setting first, okay, with all policy concentrability, and how we're gonna develop something about equivalent of VI to solve the problem. So let's do the third assumption. If you still remember in the offline setting, we kind of like make this assumption as well. This is all policy concentrability. We're saying given the data, this offline data, that is in the form of tuple of SHI, AHI, SH plus 1I, I from 1 to n. Where we see this SH, AH, is sampled from distribution that induced by some behavior policy. Okay, so SH, AH is sampled from this mu-H distribution, where mu-H distribution essentially is the distribution induced by the policy we use to collect the data. So all policy concentrability, if you still remember, kind of basically says for any policy, pi, and any state S, and action A, state action pair SA. We have the probability, if following policy pi, to visit SA at each step, divided by the visitation measure of how we collect the data, mu HSA. We say this is always upper bounded by C. Okay? So again, the meaning of all policy contributivity is for whatever state action, that as long as there exists some policy that can visit those state action pair frequently, then I'm guaranteed my behavior policy will collect those state action pair relatively frequently. Okay? The ratio is upper bounded by C. So basically, what we want is under assumption 1, 2, 3, can we develop some algorithm similar to value iteration that is going to solve the generic function approximation? So it turns out to generalize value iteration, we want to generalize. We know value iteration will be generalized to least square value iteration in the linear setting. And in the general function approximation setting, this least square value iteration can be further generalized to what we call a fitted Q iteration. So this is what we're going to introduce now. Which is called FQI. If you still remember, when we do the least square value iteration, we're essentially minimizing some square loss. In fact, in the general function approximation, we can still define this square loss. Okay. So this square loss is a function of data D and also step H. And is a function of both FH and FH plus 1. Here you can understand this F is like a Q-value function. We always talk about a Q-value function approximation. So both FH and FH plus 1 are Q-values. They're just Q-values at different steps. So we can say those are square arrows, so that 1 divided by n is the number of samples we collected. Let's say little n here. And we have SA, S prime. Those are the tuples in this data set. Okay. And we look at the square loss of FH SA, subtract by RH SA, and the max of A prime, FH plus 1, S prime, A prime, square. Okay. We can say when we do least square value iteration, we're essentially minimizing this objective where we just replace this f by linear function, because there we're doing linear function approximation. So we say this f is equal to some weight times the Fisher vector here. But this is essentially some empirical Bellman residue stuff we're like optimizing. I think you can imagine like the reason of this is somehow related to we're trying to minimize the Bellman error, and we will talk about what is the main reason behind this later. So once we have this square loss, the algorithm becomes very simple, FQI. So we're just trying to minimize, do dynamic programming and minimize this loss at every step. This is basically how we do the least square value iteration. So we're going to just do the same thing for general function approximation. So the algorithm of fitted Q iteration is the following. That we will first initialize hat h plus 1 equal to 0. Okay, so this is like I will initialize my estimate at h plus 1 step. That is a Q value at h plus 1 step. This is always 0 because there is no future reward after h plus 1 step. And then we're essentially just doing dynamic programming. Remember, value iteration is always dynamic programming from the last step to the first step. So for the step from capital H to 1, what we're doing is we will assign the Q value to be the minimizer of this square loss in this FH. And we look at the loss LD and F and FH plus 1 hat. Okay. So it's dynamic programming because we start with the value at the h plus 1 step. And once we have that value, and we can plug it in here, and we can compute the value at capital H step. And then we plug it here, and again, like we'll plug the value at capital H step here, and we compute the value at h minus 1 step. So we can like compute all the value backwards by minimizing this loss. And it's easy to verify. Like as I said, least squares, LSVI is a special case of FQI. Okay. So after telling you the algorithm, you may wonder, like, what is the relation between those this algorithm? Like, we're essentially minimizing this LD, and why does the algorithm work? Okay. So this is like basically what you may wonder. So let's first look at the asymptotic analysis. Like we look at when n go to infinity, what will happen, and which will give us some like insights on why this algorithm makes sense. So when n go to infinity, one of the very good things is we can use law of large number, where we know this loss, which depends on the empirical data. Will converge to some expectation version of this L, D, H, FH plus 1. Okay. This expectation is taking over the randomness of the data. Okay. Because in the offline data, we only have a finite number of samples. But here, but we kind of know those samples are collected from some behavior policy mu h. So when we take an expectation, we can take an expectation over this SA sample from all the possible behavior policy, so that we get rid of this all the randomness within the data collection part. Then we can look at this expectation. Okay. This is an expectation of S sample from mu and S prime sample from PH dot SA. Any question up to this point? Okay, so we look at the derivation of this expectation. So we know when we do this expectation, we can essentially replace this 1 over n summation by just one expectation. So we say this is equal to expectation over SA S prime, where SA is sample from mu and S prime sample from this transition probability. So inside, we should just copy this square arrow. But what we do instead is we will kind of like subtract a term and add a term. And plus pH, VH plus 1, SA, and subtract by VF H plus 1 S prime square, where we denoted this V value, VHF plus 1 is just equal to, it's essentially the V value induced by this FQ value. So we're taking maximization over action on FH plus 1 SA. Okay, this is just a notation. So for simplicity, so that we don't need to write the maximization multiple times. So we can essentially say this VH is what we have here, where we're taking a maximization over A prime, which is essentially just VF S prime. So what we're doing is we just subtract a term and add a term. And when we do this, this makes things a lot more comfortable. Because this is actually the TH FH plus 1. This part is the Bellman operator, operates on the value at the next step. And this part is purely the randomness of S prime. So you can essentially think this is like some bias variance decomposition. The first part is FH minus TH FH plus 1. So first part is Bellman arrow. The second one is the sampling variance due to the sample of the next states. So if you do the math correctly, you can actually realize those two randomness are independent. And you can essentially decompose this square loss to be the two term. That essentially the first term is just the first term square. And the second term is the second term square. So the cross term will actually equal to 0 because it's independent. So when we do the full decomposition, we actually have the first term square, second term square, and also 2 times the first term times second term. But because the randomness is independent, that is conditioned on this thing, we still have like this S prime random, and this is just expectation of this thing. So that's why the cross term will actually equal to 0. So that's why we only have the first term square and the second term square. So we note the first thing is essentially some distance, some Bellman arrow. Okay, we can denote it as something like FH subtracted by TH, FH plus 1, under some 2 mu distance square. Okay, so this is like a 2 norm of the Bellman arrow, but under distribution mu. So this is a Bellman arrow. And for the second term, it's also not hard to say, as I said, this is like the random variable, and this is the expectation of the random variable. So this thing is a variance term. This is an expectation of SA, sample from mu, the variance of VFH plus 1 S prime, condition on SA. Okay, so the whole randomness is due to the sampling of the next states S prime. So the variance is taking over the random variable of S prime. I think the most important thing is to notice this variance term is actually only a function of the value at the next step. This is not a function of the current step. So this term is actually independent of FH. Okay. Yes.
Wait, sorry. Why can we split up that expected value again with some two squares?
Oh, why can't we do that? In general, like you have a plus b square. Expectation of a plus b square is like equal to expectation of a square plus expectation of b square and plus 2 times the expectation of a and b, a times b, right? This is generically true. So what I'm claiming is this term is equal to 0 because essentially when you condition on A is like irrelevant to S prime. S prime is the new states, right? So whenever you condition on the first term, the second term still have expectation equal to 0. So you can think in this case, what you can do is that is the expectation of B condition on A. Something like that, times A times this, right? And this term is actually equal to 0. Just because the expectation of S prime, the A term is irrelevant to S prime. And this is just purely about the randomness in the S prime, and actually has mean 0. So the cross term actually cancel out. So hopefully I convince you the reason we look at this square loss, the similar, like this loss we kind of used in FQI, and also in the least square variation, is because inherently it is just equal to the Bellman arrow and some variance term, okay? Variance term and actually irrelevant to FH. You can think it's basically just a Bellman arrow plus some constant, because this term is independent of FH. So now we can understand why FQI actually works. So FQI, when n goes to infinity, what we're essentially doing is we're saying we will do FH at H. We say it's an argmin of F, and LDH, F and FH plus 1 hat. When n go to infinity, we say this has a concentration, or like a strong law of large number. So this loss becomes something in expectation. Okay? This is roughly equal to argmin of taking expectation of this loss. And we also know this is like a minimization over the first argument. And the second argument, the variance, is actually independent of the first argument, independent of FH. So when we do the minimization over F, second term doesn't contribute to the minimization. So we're essentially just minimizing the first term, which essentially says we're also doing the argmin of FH fh minus th fh plus 1. This is the Bellman arrow. Now you can know this, when we look at the square laws, up to some variance, we're essentially just minimizing the Bellman arrow. And this is why we're doing this algorithm. It's very straightforward. In the tabular setting, we're saying Bellman arrow is 0, and in the function approximation, we're just trying to minimize this Bellman arrow. The hat. So this is all when n go to infinity. When n is not infinity, then we cannot do this. Okay. So the next thing is now we're minimizing the Bellman arrow. But why minimizing Bellman arrow still makes sense in this generic function approximation is because we assume the completeness. Okay. We know since we already know this fh plus 1 hat. We solve this fh plus 1 hat by this equation. It's essentially, we find a function within this function class. So we know this fh plus 1, by doing this dynamic programming, is also in the function class in the next step. And then by completeness, closeness, this is assumption 2, so we know this th fh plus 1 hat. Because this fh plus 1 hat is in the function class in the next step, so after applying the Bellman operator, it should be a function in the function class of previous step. Since this by itself is a function in this function class, so we know the minimum value of this square loss is exactly equal to 0 because this thing is inside this function class. So when we do the minimization of this square loss, we can essentially just take the f equal to precisely this function and to make this square loss exactly equal to 0. With minimizer, so essentially, this is saying when n go to infinity, when we minimize the Bellman arrow, we're essentially just solving for some function that satisfies the Bellman equation, Bellman update. So therefore, since we know the fh plus 1 in the very last step is always equal to 0 and equal to the q value, optimal q value. And then optimal q value satisfies the Bellman equation. F hat also satisfies the equation, Bellman operator equation. So this kind implies fh hat is just equal to q star for any edge. Okay. So this is the intuitive reason why fqi works if we have infinite number of samples. Okay. Any questions about this so far? Everything we talk about so far, although it's a little bit mathematical, but it's relatively simple, we're just minimizing the square loss. And we kind of understand the square loss can be decomposed to the Bellman arrow plus some fixed term. So everything boils down to we just minimize the Bellman arrow, and when n go to infinity, we're essentially just solving the Bellman equation. So now the question is, if we don't have infinite number of samples, then everything has error. We are no longer just exactly solving the Bellman equation. We're only solving, like approximately solving the Bellman equation. In that case, how many samples? Do we need? For FQI. To find epsilon optimal policy. So I will directly give the result for this. Since this is an offline scenario with all policy constructability, you can imagine the analysis roughly follows from the analysis of all constructability value iteration, but with the modification to do this general function approximation with this kind of decomposition. So the theorem one says, suppose my value function class is bounded. That is fh, sa is always bounded by b for any h, s, sah, and f. Any fh in fh. Then this fitted Q value iteration, fitted Q iteration can find epsilon optimal policy with probability at least 1 minus delta within following number of samples. O tilde, O of poly H against some polynomial horizon, and B square C log max H FH over delta over epsilon square. Samples. Okay, let's look at what kind of a quantity this sample complexity depends on. So B is the bounds on the function value. You can think this is also, again, something H or something. So this is just some upper bounds. So the important thing is this C, which is the concentrability coefficients. Okay. This is when we assume the offline setting, we always have this dependence. Even in the offline value iteration scenario, we also depend on this concentrability coefficients. And what's more important is instead of having some state action number dependence or dimensionality, what we have now is something like log f, okay, where f is the function class. And for here, we're assuming, for simplicity, assume the function class is finite function class. So this is the cardinality of function class. So the most important thing you realize is, in addition to this constructibility coefficients, we only depend on the log cardinality of the function class. This is actually a standard thing in statistical learning, and especially when we do the union bound, you kind of like realize the union bound has this exponential thing. Whenever we have concentration and we have some union over a thing, then we kind of we always pay this log cardinality stuff. Yeah, this is a very good question. So we'll actually not talk about it. So this log f is essentially the new complexity measure for function class. So a lot of times you may think, okay, this seems like not very useful because for a lot of value function class, it's kind of like infinite function class. For example, even when we consider the tabular setting, we kind of look at all the q value for all the possible q value for all the state action pair. And in that case, like q value can take any real value from like 0 to h. So in that sense, we have infinite number of functions, and this is going to infinity. But in terms of reality, is we can always do some discretization for the function class. So the reason is eventually we only care about epsilon optimal policy. So we don't really care about getting q value to be infinite precision. We kind of probably just only care about approximate q value up to some epsilon accuracy or something. So in that sense, if we can like discretize q value class is up to some epsilon accuracy. Usually it's enough so that we don't need to consider the infinite class. We only need to consider some finite class that is epsilon accurate. So we can consider something like a tabular setting. First, in a tabular setting, we know for each state action, we can probably like pick h over epsilon possible values. Essentially, it's for each state action pair, we're discretizing the value from 0 to h by epsilon accuracy, do epsilon grid. So the total number of grid is like h over epsilon. And we know we have SA different possible state action pair. So the total number of total number of function, cardinality of function class is like h over epsilon to the SA. And we know if we take the logarithmic over this cardinality, this is something like O tilde SA. Okay. So up to some logarithmic factor is just SA. So this is something totally acceptable. And we can also show in the linear case, you can also do some similar discretization for the linear function up to some epsilon, and where you can also show the linear case, the log f is roughly something O tilde dimensionality. So this is like a very reasonable complexity measure for function class. I guess I will omit the details on how to prove such a thing is true. And yeah, any questions about this offline part? Yes.
You can't just like, even if you discretize by like epsilons or whatever, you still can't take some arbitrary function over all of space or whatever, like an infinite SA dimension, right? Like that would be over.
You cannot take an arbitrary function, yeah. But the point is you don't need to take an arbitrary function. Yeah. You just need to take the function over the grid, over the discretization grid you have, and that's enough to get.
Like what if like the states are like negative infinity to infinity and others?
You mean the value is negative infinity to infinity?
I mean, like, I guess what if there's like
States is negative infinity.
states,
It doesn't matter for linear function. For tabular case, for tabular cases, only only have s different states. So there is like no negative infinity states. But for linear case, it only matters if you like discretize the feature space. And we know like in the linear MDP, for example, the feature space is always like simplex or some like hyperplane. So you cannot go like very wild.
an arbitrary non-linear function, like if you have infinite number of states, then how would you discretize that?
I think then it's essentially you don't discretize the states, you discretize the function. So I think the whole point here is the function itself has some bounded complexity. So you can think if my function is a linear function, or my function is like this table with only SA entries, so the log f is always bounded. So in your case, like for example, if state is negative infinity to the infinity, but if you're saying after the states, like you can map the states to some like linear feature in some certain feature space, and I'm only care about learning the weights, then I can still apply something like that. So for more general, beyond the linear setting, you can also say for some like neural networks or some like more complex function, the formal notion is called a covering number. Essentially, you just want to discretize this continuous space with some certain grid, and so that the grid is able to cover the whole space with some epsilon neighborhood ball, and this is enough. And this is like a well-used notation in the learning theory.
So you're saying even if there are infinite number of states, there's some feature space with finite dimension that you can then discretize?
Yeah, this is like one way to do that. Or if your function has like a small covering number, as I said, you can essentially your function class can be represented by some small number of representative functions so that they're epsilon close to each other, and then you're good. Any other questions about this? Okay, so this is we're talking about the very basic thing for all policy constructibility and FQI. So by analog, you can also imagine there will be some equivalent version of doing pessimistic. And also one policy constructibility. It turns out this thing is not that straightforward compared to the tabular setting, but it's doable with a little bit more complicated algorithm. So we will like skip this part here, but it just let you know you can also kind of like deploy some similar strategy of pessimistic, also do the one policy constructibility. So we'll talk about online scenario for now. So I think online scenario is more exciting because this offline scene and online scene is quite different. So we know offline FQI. Requires access to representative data. Essentially, this representative data is, we mean it by like we require this all policy constructibility condition. So whether such data exists by itself is also a very challenging problem. Like usually we don't really know whether all policy, if all policy constructibility is going to satisfy it with some small c. If c is very large, then this whole guarantee like becomes very vacuous and it's not very good. And also the other thing is this is like completely about the offline scenario. When we do the online scenario, can we, like under what kind of condition can we do exploration? Can we do exploration? in general function approximation. To set things start, we just remember we have assumption 1 that is about realizability. And we also have assumption 2 that is the completeness. And also, we're more saying eventually we have the log f is small. Okay? Log f cardinality is small. So that we're saying the function class has some like bounded complexity. It's not like a completely wild function class, like with infinite complexity, so that we cannot do anything about it. So the question is whether those 3 conditions are already enough for us to do like online reinforcement learning or do exploration, so that we can completely ignore the all policy contributory thing for offline and achieve some like guarantees. It turns out, though, the answer is no. So this is not enough. Those assumptions are not enough. To establish sample efficient guarantee. Sample efficient guarantee in terms of we want to have some guarantee of polynomial samples. Under general function approximation. So it turns out what we need is we further need some complexity measure to essentially like measure the complexity of doing exploration. So we need something to replace all policy contributory. And to So there has been a lot of study. It turns out there have been a lot of study to talk about what kind of complexity measure we should use for like this exploration. Like even in the bandit scenario, like people have some eluded dimension or something like that. So today we will talk about some relatively simple, but I think it's very insightful. It kind of carries out the major thing in the reinforcement learning of how to adapt the complexity measure of bandits to like a reinforcement learning part. So what we will introduce this complexity measure for exploration is called the Bellman rank. Okay. And this is introduced in a previous paper with title called contextual decision process. With low Bellman rank. pack learnable. Okay, so to introduce this notion, we first denote a few notations. That we denote the function class. F, this is a big F, to be the Cartesian product of F1, F2, till Fh. So we're still in the set for every step. We have a function class for the Q-value function. But this capital F, this big F is just the Cartesian product of all function Q-value function choice for every step. And we also use the value function. F in F, where F is just denoted as F1 till F capital H, with each Fh is inside the curly Fh. Okay? It's just the tuple notation of F. Whenever I do some Q-value without the index of the step, it just means it includes every steps. And similarly, we can also define the greedy policy. Induced by value. Essentially, because for simplicity, we assume that number of actions is finite. So what we're doing is when we look at some function value for each state, we can do argmax over the action for that state. So this defines the greedy policy pi f. And when we say this pi f is actually, again, a tuple of a greedy policy at every step. So with this notation now, we can introduce the Bellman rank thing. So first, we need to define the average Bellman arrow. With a row-in policy pi. So for any f, for any value function in this Cartesian product of the function class, and any policy pi, we can define the following quantity, which is average Bellman arrow. Which is a function of first the value function f, and also the row-in policy pi. Okay. So this is defined as the following, that we take expectation, and we look at the following quantity. It is the Bellman arrow, so we will look at the value function at h step, divided as subtract by applying Bellman operator on the value function of the next step on the SH edge. Okay, so this is the Bellman arrow. And the most important thing is about what is distribution. So far, this f are both coming from this f. Those are just some coordinate of this f function. But where is this pi coming from? So this expectation is taking expectation over the state action at h step. So we need to specify what is the policy we use to reach this h step. So it turns out what we're going to use is use this pi policy for the first step till h minus 1 step. And in the h step, we will use the greedy policy of f. Okay. So this is indicating that we will use this pi policy, rolling policy pi, for the first h minus 1 step. And in the last step, we will use f. So you can think this whole thing will first roll in with this policy for the first h minus 1 step. And then suddenly everything will switch to f. Okay? We'll use the greedy policy of f, and we will evaluate the Bellman arrow on this f function. Since in the first h minus 1 step we're using the pi, so we can basically conclude that SH is generated using policy pi. So this is why we think pi is the roll-in policy. But because at h step we're acting according to pi f, so AH is the first action that we use different policy. Is chosen according to pi f. So once we have this notation of the average Bellman arrow, it's easy to define a Bellman rank. Essentially, we can consider epsilon h, or big epsilon h, be a matrix in Rf by f. That is a big, very big matrix where each row is corresponding to one function, one q-value function, and so this big matrix is indexed by two functions in the function class. And we see this f prime entry of this big matrix is precisely the average Bellman arrow defined by evaluating. Essentially, it's a Bellman arrow evaluating on this f, but with rolling policy of, that is greedy policy of pi f prime. Okay. So we define a big matrix, looks like this. Then the Bellman rank of this MDP, we call it M, with function class f. is defined as the maximum rank of this matrix over all steps. So the Bellman rank essentially says this matrix defined by this average Bellman arrow, which kind of decouples the rho-in policy with the Bellman arrow we evaluated, with the Bellman arrow function we evaluated on, need to be low rank. And typically, we will use some equivalent characterization. So equivalently, M has Bellman rank D means the following, that means there exists some map phi and psi both maps function f to some d-dimensional space, so that for any f and f prime, the average Bellman arrow evaluated on f with rho-in policy pi f prime can be decomposed as phi f prime and psi f. And this is like a d-dimensional thing. So this notation is a little bit abstract, but we will, in the next lecture, we'll illustrate like why this rank, like notion of rank, is actually something very key in govern the complexity of exploration in this reinforcement in MDP scenario, and why in all the previous examples we did so far, like for example in the tabular setting and the linear function approximation, we never talk about this Bellman rank. And we will show actually because for those scenarios, the Bellman rank is actually already guaranteed to be small with those structure. Like with linear structure, with tabular structure, you can already show the rank is small. And we will also talk about what kind of algorithm we can deal with all the problems with low Bellman rank.